Hello all and welcome to Physics with Pranav. If you're new to my channel, I'm Pranav. I used to be a CAIE science and math student. I've tutored GCSE physics and A-level physics students from around the world, and I'm an IGCSE world topper in science from back in 2013. In my videos, I present to you a simple three-step approach that has helped me and my students score excellent grades in our exams. The approach is essentially, first, we look at the key concepts that have been tested in recent past papers. So I provide you with data from actual past papers and the questions and concepts that are tested from each topic. The second thing is to gain a solid foundation in these key concepts so that you feel comfortable applying them to past paper questions. And then finally, we'll actually look at how these concepts are applied to past paper questions so you feel confident when you actually go and take up your exams. So the way my videos are structured is I have based them around the CAIE curriculum, and the different chapters that the videos are split into are also based off of the CAIE curriculum. That said, I do have to say that if you are a student from any other GCSE curriculum like AQA, Edexcel, or OCR, I still think you will gain a lot of values from these videos because a lot of the concepts covered tend to overlap a fair bit, and you will also really benefit from the methodology I use when it comes to solving past paper questions, irrespective of what curriculum you study in. That said, in this video, I will be looking at Chapter 8, which is Work and Power of the CAIE curriculum. This chapter, as mentioned when we were looking at chapters 6 and 7 around energy, is very closely linked to the concepts of energy. So some of the questions that we solved for the topics of energy involved applying the concepts of power. And equally, we will see that when we look at past paper questions in this particular chapter, we will also be using the concepts of energy quite closely. I usually split my videos into two. In one set of videos, I have a look at the key concepts tested and dive into detail so that you feel like you have a solid grasp of the foundations of these concepts. And then another set of videos, I will be showing you how to apply those concepts to past paper questions, both the multiple choice papers as well as the theory papers. In this video, for Chapter 8 of the CAIE curriculum, Work in Power, we will be looking at what the key tested concepts were from recent past papers, as well as diving deeper into those concepts. So without further ado, let's take a look at Work in Power. So in Chapter 8, Work in Power, I have looked at recent past papers from 2020 and 2022. I've seen both Paper 2 and Paper 4. Paper 2 is a multiple choice paper. Paper 4 is a theory paper. I've seen all three variants, 2.1, 2.2, 2.3, as well as 4 and 4.2, 4.3. I've looked at the summer, the winter, as well as the Feb-March papers to try and get the full breadth. So the most commonly tested concepts in this chapter are, as one might expect, work and power calculations. You have lots of calculations around that. And then we can see that this is the most commonly tested concept in both Paper 2 and Paper 4, appearing in 13 out of 21 past papers that I looked at between 2020 and 2022 in Paper 2, and 5 out of 21 in 2020 to 2022 for Paper 4. The next most commonly tested concept is describing work done and power in different situations. So we can see that a third of Paper 2s have asked questions around this. So they will give you a scenario and they'll expect you to describe how the work done and the power has changed in these situations. We can see that this concept is not that common in Paper 4. And then finally, we have calculations around efficiency. So we did look at this briefly when we were looking at the concept of energy. So we have efficiency calculations for power as well. And we can see that it has appeared in 5 out of 21 questions in Paper 2, as well as 3 out of 21 questions in Paper 4, making it the second most commonly tested concept in Paper 4. And I think it's fairly obvious that for this chapter, there are more questions in Paper 2 than there are in Paper 4, which is why I put that up in bold there. We can see that irrespective of whether we're looking at Paper 2 or Paper 4, the most commonly tested concepts are work and power calculations. I also want to mention here that in this particular topic, it has a lot of overlap with the topic of energy, which we explored in our earlier videos. And as I mentioned in those videos as well, there are quite a few questions on energy which will expect you to use the concepts of work and power as well. And you find the same when we look at past paper questions for work and power. So it's just something to be wary of. These topics are quite closely related to one another. So let's now jump into the actual calculations for work in power then. So the first thing that I want to explore is obviously what work done is. And work done is essentially the force multiplied by distance moved in the direction of force. Essentially, if you apply force to an object and the object moves in the direction that you apply the force to, then the work done will be the product of the force multiplied by the distance moved by the object. So obviously, the greater the distance it moves, the more work you need to do, right? Because if it's a same object and you're trying to make it move a greater distance, then you have to put in more force. But equally, the amount of work that you do will be great, and that is just how I would try to conceptually think about it. If the distance that the object needs to move, you probably have to put in more force. You also probably have to do a greater amount of work. Equally, if the object still moves the same distance, but you put a greater amount of force, you still end up doing a greater amount of work. So the way I'd like to think about it visually is here we have an object which has a mass of m. It has a force F acting on it. The force acts over a period of time t, and during that time, when the force acts on it, the object moves a distance d, as shown within these two dotted lines. Because the force is acting on the object in this direction, and it's moving a distance in this direction as well. The distance is moved in the direction of the force. Therefore, the work done is simply going to be the product of the force and the distance, or F multiplied by d. You will have instances where the force is not quite acting in the direction in which the object moves. So it's possible that the force is probably acting at an angle to this arrow that we have here, and that is the initial force, and the object still moves a certain distance in the region marked here. So in that scenario, you'd have to find the component of the force that acts in the direction of motion of the object. So in this case, the direction of motion still remains the same. So what you would have to do is, if the force is acting at a certain angle, like like that or like that, you would have to find obviously this component here, which is currently now shown by F. And if you were to use trigonometry for that, that component would be the initial force that is applied multiplied by the cosine of theta, where theta is the angle to the direction of motion of the object the force acts in. So if the direction of motion is this horizontal here, and the force acts like that, the angle is essentially the angle between the horizontal and the force. And if you use trigonometry, if you have done math, then you know that this particular component would be F cosine theta. But then again, at the GCSE level, most of the questions will typically involve the object moving in the direction of the force. It's going to be rare that the object is either going to move in a different way, or the force is going to act at an angle or in a slightly different direction to the direction of motion of the object. So it's not something to worry about too much in your GCSEs, but if you do get the occasional question, it's important to get that component of the force in the direction of motion of the object. So we know then the work done is a product of the force and the distance. Now, if we think about the units for work done, it's going to be Newton meters, right? Because force is measured in newtons, that's the SI unit for force. Distance is measured in meters, so it would have units of Newton meters, essentially. But we know the force is also mass multiplied by acceleration. We know that the SI units for that would be kilogram meters per second squared, because mass is measured in kilograms, acceleration in meters per second squared. So essentially here you're going to have kilogram meters per second squared multiplied by meters, or you're going to have kilogram meter square divided by second square. Now if you think about those units, either Newton meters or kilogram meter square per second square, and then compare it with the units of the energy forms that we know. So if we look at kinetic energy, for example, we know that kinetic energy is half mv squared, or half mass times velocity squared. So half obviously doesn't have any SI units because it's a constant. But then if you look at mv squared, m has the units of kilograms. V square has the units of, V has the units of meters per second. The square of that is meters squared per second squared. So essentially the unit of kinetic energy, which will also be the units of any other form of energy, gravitational potential, electrical, chemical, you name it, is going to be kilogram meter square per second square, which is the same as the units of work done. So essentially work done can also be measured in joules, as energy is. And I think the important thing that we're trying to say here is that work done is the same as the energy transferred, or the energy released, or the energy absorbed. So work done is essentially energy. So I think that is what I'm trying to say, which is what I've stated here. Now, power is the rate of doing work or the rate of transferring energy, because obviously, well, work done is an energy transfer. How quickly you do it will determine the power. So obviously, power is then work done per unit of time, or energy transfer per unit of time. We've already had a first-hand experience of this when we were looking at past paper questions for the topic of energy, where there will be some energy transformation happening, either the kinetic energy is raising or falling, or the gravitational potential energy of an object is raising or falling, and then it happens over a period of time, and then you would then be able to calculate the rate of transfer of energy, which is also the power, and power is measured in watts. Obviously, you can also have kilowatts and megawatts and higher units of it, or microwatts for lower units, but ultimately it's measured in watts. It's joules per second, or Newton meters per second, however you want to think about it. But joules is typically the unit of energy or the unit of work done. So I would like to express it as joules per second. So that is the units of power. But the common units used is watts. So just something to be wary of. I also want to mention that work done can be measured in what's called kilowatt hours. So what do we mean by that? So if you think about it, if power is work done per unit time, then work done can also be expressed as power multiplied by time. Yeah. So if I just change the subject of the formula, if I keep the work done there and take the time to the other side, the product of power and time gives you the work done or the energy transferred. So we know that power can be measured in watts or kilowatts or megawatts or whatever. We know the time, although its SI unit is seconds, it can be measured in minutes, it can be measured in hours, it can be measured in days. There's obviously different measures for time. So when you tend to multiply the power in kilowatts with the time in hours, you get a unit called kilowatt hours, and that essentially is a unit of work done. It's a unit of energy transferred. So if you do see the terms kilowatt hours, you're actually not talking about power, because power would just be kilowatts. It's kilowatts multiplied by the hour, and that essentially is power multiplied by time, which is work done. Hopefully that makes sense. So the next bit we're going to be looking at is efficiency. So we have looked at efficiency when we looked at the concept of energy, where in the concept of energy, efficiency was the useful energy output divided by the total energy input. Then if you multiplied that by 100, you got an efficiency percentage. In this particular scenario, what we have is an input power, essentially, instead of input energy, and we've got an input power of 100 watts. We've got a wasted output of 10 watts. So if you think about this as the mains electricity, you're giving 100 watts of mains electricity to, say, like a heater, for example, and the heater is crackling a bit, it's got a bit of sound, so there's 10 watts that's wasted. Maybe it's got a light coil, which shows that it's on or something, so that's a bit of energy wasted. But then most of the energy, 90 watts, is doing what it's meant to do, which is heat the surroundings up. So the efficiency is the useful output power, which is that, in this case 90 watts, divided by the input power, which is that, which is 100 watts. Or efficiency is 90 divided by 100, or 0.9. If you multiply it by 100, you get the efficiency percentage, or the percentage efficiency, and that is around an efficiency of 90%. And again, I've just left the note here that efficiency can also be equated in terms of energy. So that is just something to keep in mind. I know for this topic, the other thing that was commonly tested is describing work done in power in situations. In fact, it's the second most commonly tested concepts from this chapter, especially in paper 2s. But we will not be exploring it here in the key concept tested. Instead, it is better to have a look at examples of questions where we do describe work done in power in situations. So I will be making videos where I will show you how to apply the concepts in this chapter that we've explored in this video to paper 2 questions and paper 4 questions, and I will leave the links for those videos in my description below. But I hope you found this useful. Please share with others who you think will find it useful as well, and then if you gain value from this video, consider liking and subscribing. Thank you very much. I will join you in my next video.